Almost every guide about running A on your own computer opens with the same line. You need a GPU. And if you do not have one, the tone usually shifts to pity, like you have already lost before you even started. I ran straight into this wall myself because the machine I wanted to test on does not have a fancy graphics card sitting in it. It is just a normal desktop, the kind of thing most people actually own, not a custom-built rig with a glowing card the size of a brick inside it. So instead of going out and spending real money to fix a problem I was not sure I even had, I asked a simpler question. What actually happens if I run a language model on the CPU alone, with no GPU involved at all? Not in theory, not what some forum post claims, but on my own hardware with a stopwatch in my hand. I tested it properly on real models of 3 different sizes, and the answer is far more interesting than either side of the argument lets on. It is not a clean yes, and it is definitely not a clean no. It depends, and the things it depends on are exactly what I want to walk you through. First, let me explain why everyone reaches for a GPU. The reason the GPU gets all the attention comes down to 2 things: memory and math. A language model is basically a giant pile of numbers called weights, and to generate a single word, it has to push your text through all of those numbers and do an enormous amount of multiplication. We are talking billions of tiny calculations for every single word it produces. A graphics card is built to do thousands of those little multiplications at the very same time, in parallel, which happens to be the exact shape of this problem. It is almost like the hardware was waiting for this job to come along. A CPU, by contrast, is built to do a smaller number of things very quickly, one after another, with a handful of cores working at once instead of thousands. So on raw throughput, the GPU wins, and it is not even close. That part of the hype is completely true, and I am not going to argue with it. But throughput is not the whole story, and the gap between what the benchmarks say and what you actually feel sitting at the keyboard is exactly what I wanted to measure, instead of just repeating what everyone else says. So what does CPU only really mean? When you run a model on CPU only, the weights get loaded into your normal system memory, your RAM, instead of into the special faster video memory that lives on a graphics card. Then your processor cores grind through all that math to produce each word 1 token at a time. The single biggest thing that decides whether this is even possible is brutally simple. Does the model fit in your RAM at all? If the model is too big for the memory you have, it simply will not run, or worse, it spills over onto your disk and crawls so slowly that it is completely useless. So before anything else, before you even think about speed, this is a memory question. How much RAM do you have, and how big is the model after it has been compressed down? That compression step is called quantization, and I will come back to it in a bit, because it turns out to be the single most important lever in this entire test. For now, just hold on to the idea that the model has to fit, and fitting is the first gate you have to clear. Let me tell you about the machine and the models. Here's exactly what I ran this on, so you can map it to your own setup at home. A fairly ordinary desktop, nothing special, a recent 6-core processor, the kind you would find in a normal office computer, and 32 gigabytes of system RAM. No discrete graphics card doing any of the work at all. For the software side, I used a small local runner that loads a model and lets you chat with it from the command line. The kind of thing anyone can install in a few minutes without being a programmer. Then I picked 3 models on purpose to cover the range. A tiny one, around 3 billion parameters. A middle-sized one, around 8 billion. And a genuinely large one, around 70 billion. Mostly just to watch it break and see where the ceiling was. Each one was quantized down so it would actually fit in memory. And then I did the boring, useful, unglamorous thing that most demos skip. I asked each one the same handful of questions, the kind of everyday tasks I would actually use a model for, and I timed every single part of it carefully. Now here are the actual numbers. Let me give you the 2 numbers that really matter, because they measure 2 completely different kinds of pain. The first is how long you wait before the very first word even appears on screen. The second is how fast the words come out after that, measured in tokens per second, where a token is roughly part of a word. On the tiny 3 billion model, the first word showed up in about a second, and then the text streamed out at a pace that honestly felt fine to read along with, a little faster than I could comfortably read it. On the 8 billion model, the first word took a few seconds and the speed dropped to something more like a slow but steady typist working away. Still usable, just not snappy, the kind of thing you wait on without getting annoyed. And on the 70 billion model, well, the first word took the better part of a minute to arrive, and then each word crawled out so slowly that watching it happen was almost funny. Technically it worked, it produced a correct, thoughtful answer, but practically it was completely unusable for anything where a human is sitting there waiting on it. And that gap between the small model and the big one is the whole lesson in one picture. It was not that the big model was wrong, it was that the big model was right far too slowly to matter. The tiny model, the one most people would dismiss as a toy, was the one that actually felt good to use. So if you take only one thing from these numbers, let it be that on a CPU, the smaller model that answers right now usually beats the bigger model that answers eventually. Speed you can feel is worth more than a few extra points of cleverness you have to wait a full minute to receive. So where is CPU only genuinely fine? Here is the part the hype crowd always skips right over. For a huge number of real, everyday tasks, CPU only is completely fine. Genuinely fine, not fine with an asterisk. If you are running a small model to clean up text, to summarize a long document, to classify a big pile of emails into folders, to pull structured data out of a mess of handwritten notes, the small and medium models on a CPU do all of that perfectly well. And the key reason is that these jobs are not a live conversation where every second of delay is painful. They are batch work. You hand the machine a stack of inputs, you walk away to do something else, and you come back later to the finished results sitting there waiting. Nobody is sitting at the screen drumming their fingers. And there is a second, quieter win that has nothing to do with speed at all. It all runs locally on your own machine with no APT to manage, no per request bill ticking away, and absolutely nothing about your data ever leaving the building. For private documents that you would never in 100 years want to paste into someone else's cloud, that one fact alone can be worth accepting a slower model. And here is exactly where it falls apart. Now the honest other side, because I am not going to pretend CPU only is some secret that everyone is hiding from you. It falls apart in three clear, predictable places. The first is sheer size. The big models, the ones that genuinely reason better and handle the hard questions, are simply too slow on a CPU to use interactively. You saw that with the 70 billion test. The second place is long context. The more text you stuff into the prompt, the more math there is to do per word, and on a CPU that cost piles up frighteningly fast, so a model that felt perfectly okay on a short question can grind almost to a halt the moment you feed it a long document. The third place is anything real-time. If you want a voice assistant that answers the instant you stop talking, or a coding helper that keeps up live as you type, the CPU just cannot deliver that snappy back and forth, no matter how you tune it. For those three things, a GPU really is the right tool, and I would be lying to you if I said otherwise. Quantization is the real secret here. If there is one single idea to take away from this whole test, it is quantization, because it is the thing that makes any of this possible at all. Remember that the model is just a giant pile of numbers. Quantization stores each one of those numbers using fewer bits, so the whole pile gets dramatically smaller and much lighter to compute on. A model that would need way too much memory to run at full precision can shrink down to a quarter of its size or even less. And that shrinking is the entire difference between fitting in your RAM and not running at all. There is a trade-off, of course, because there is always a trade-off. Squeezing the numbers down does cost a little quality, and if you push it too far, too aggressively, the model gets noticeably dumber and starts making more mistakes than it should. But a moderate, sensible amount of quantization is close to free in practice. You barely notice the difference, and it is the thing that turns CPU only from a cute party trick into something you can genuinely lean on. Picking the right level for your particular hardware is honestly most of the real skill here. The way I think about it now is that quantization is the dial that lets you trade a sliver of brains for a lot of room. A little turn costs you almost nothing you would ever notice. A hard crank in the name of fitting some huge model into too little memory will leave you with something that runs but answers like it took a knock to the head. So the move is to find the biggest model that fits comfortably at a sensible level of quantization, and then stop, rather than chasing a bigger model squeezed so hard it barely thinks straight. Let me be honest about cost and power. People always want to know what it costs. So here is the plain, unvarnished version. The model files themselves are free to download for the open ones I used, and running them on your own machine has no per request fee at all, which is genuinely nice compared to paying by the token for everything you do. But I want to be really careful here, because this is exactly where people start telling each other comforting lies. The hardware is not free, the electricity is not free, and the CPU pinned at full load for a long batch job does pull real power and does noticeably heat up your room. It is cheaper than a lot of people assume, but it is not magic, and it is certainly not zero. And I would never tell you it flat out replaces a paid cloud model for the genuinely hard stuff, because for the most demanding tasks, the big hosted models are still clearly ahead. This whole thing is about knowing which tool fits which job, not about declaring some grand winner and pretending the other side does not exist. So should you bother with CPU only? Would I tell everyone to ditch the idea of a GPU and run everything on a CPU? No, of course not. That would be silly. If your whole thing is fast interactive chat with a big capable model, then save up and get the card. It is simply the right call for that job. But if you have an ordinary computer with a decent chunk of RAM and your real needs are summarizing, sorting, extracting, and tidying text quietly in the background, then CPU only is not some sad compromise you should feel bad about. It's a perfectly good setup that costs you nothing extra and keeps every byte of your data at home where it belongs. The honest takeaway from all my testing is this. The question is never just can you run A without a GPU. The real question is always which model, at which size, for which job, and once you frame it that way, a plain CPU does a whole lot more than the guides ever give it credit for. I am going to keep poking at the limits of local AI on modest, normal hardware in future videos. If that is your kind of thing, subscribe and follow along, because there is a lot more coming. Thanks for watching, and I will see you in the next one.